Today we're going to be talking about filters, and the filter follows the mixer here. So currently the way we have it set up is we look for incoming changes from our MIDI controller, that's the keyboard. Then we either save those for the sequencer or modify the frequencies for the portamento, pass them off to the oscillators, then mix them together. And the filter takes what's mixed here and filters out some of the frequencies that we don't want. Hence the subtractive part and subtractive synthesis. So here, we'll add the filter. All right, we'll go ahead and make the thing for that. Declare it. And then we'll come down here after mixer and add it. Let me put this here first. Mixed is it should be the name of what's coming out of the mixer. Yep. Okay, N is what's going into the filter. We need to find the proportional frequency between the knob's position that we're going to be physically turning and the actual frequency that gets set in here. So there's an equation for that. So this is basically the equation. We're going off some frequency scale that we'll have to create. And basically we take a knob level. So as we turn a physical knob, we get some sort of value back that we interpret. And then we multiply it with this low-pass filter scaling, and then our total filter level, so it's all just scaled, and then this all gives us an index. And then we pull out from the filter scale exactly what filter frequency that the knob's set at. Currently this is so that as you turn the knob, all the way low means you're basically nearly at 0 hertz. And all the way up goes right to about 20 kilohertz. So it's the full hearing range that a standard human should be able to hear. And this high frequency is the same thing. The only difference is that it just goes to a different filter, a high pass filter. So the first thing that we should do is create this list. And we'll do that in our tables. That's one of the tables that we make. Alright, so here's generate tables, and we'll go ahead and throw this up. Just throw it up. Alright, so this is just a log scale, 2 to the power of, 2 times 10 to the power of something. So yeah, that's all it is. And so now we have these available to us. Alright, there's a certain kind of algorithm that I'm going to be using to perform the filtering, and it requires, instead of using the actual filter, kind of a scaled form of the filter based on our sample rate that we're pushing out to the DAC. And this just basically allows us to work in this discrete domain. There's a couple different ways that you can do filtering. In this case, I'm using this sort of algorithm that I'm about to show you. It, as far as I could tell, uses the least amount of calculations than the other methods that I could find, and it works pretty well. At first I tried just a first order system, like a heat dissipation equation, but I wanted to actually have some resonance capabilities, and so you can't just string 2 of those heat dissipation equations together. So at some point I had in here also a spring mass damper system oscillating back and forth, and I was simulating it, and its position was the waveform, but that took also too much calculations. So then I switched over to this. So the filter I'm about to use is, the physical filter is called a Sallen-Key filter. Sallen-Key filters look something like this, where basically you have a low-pass filter and then a second low-pass filter. So this is a second order Sallen-Key. And by changing the gain on this op-amp here, you can change the resonance. I believe, if I remember correctly, that's how it works. I couldn't find a good equation for a filter, so basically I took this filter and I took a second order version of this filter, and I just wrote down the equations for this diagram and came up with the system dynamics, and then stripped it out so that way there were fewer calculations I had to do, and that's basically what I use as a filter. So this is the equation for a single high pass filter. So I do have a high pass filter in this synthesizer, which is a little uncommon, but there are some neat things you can do with it. Following this is a low-pass filter. So the low-pass filter looks very similar. And then after this, we have our second low-pass filter. So at this point, we have two low-pass filters back to back. The more filters you have, the more low-pass filters you have, the smoother what's passed through will sound. This next thing I'm going to put in here is actually going to be for the resonance. So at a normal Salon key topology, if you crank up the gain of that op amp and feed the exit of the filter back into the input and magnify it, then you can eventually get it to self-resonate. And so that's basically what this handles. What this also does is it cuts it off as well. So when the filter starts resonating and it's doing some self-oscillations, it doesn't go past that, become unstable, and blow up our values. So you can also do some distortion here. So if you crank up the other knob, then you just distort the sound. So you increase its amplitude and cut off the caps of it. And that's basically all that's happening there. And then we end with two passive filters, basically. And yeah, that's actually it for the filter. At this point, we could load up this code and try it out. First I have to change something. So filtered is now the output. And instead of outputting the mixed signal, we'll output the filtered signal. Let me increase the volume a little bit. So low pass filter, it's a third order low pass filter. It also is an active filter, the way it's coded up. So it also includes the resonance, and it includes the sort of a distortion that just does perform some clipping. So low pass filter first. And you can see as I do that, okay, so you can see what happens when I adjust the low pass filter. It gets rid of those sharp edges. Those sharp edges are only possible with really, really high frequency content signals. So as you cut away the high frequency content, you essentially smooth out what it looks like. And then the high pass filter is the opposite. It gets rid of the low frequency content. So as I increase the high pass filter, you'll see that the part where the big jumps occur stay, and the sort of steady state climb in the saw wave disappear. So that's that. Then onto the resonance. The resonance does require some filter action, so I'm going to have to filter it a little bit. And then I'll slowly increase the resonance. Right now I've taken I'm going to try and talk during this. I've taken my hand off of the keyboard. Right now the oscillators are not running. It's actually only the filter running. And so with resonance, if you saw the smooth parts started to have oscillations in it, that's the whole feedback working. And the waves start appearing in the straight part after there's a jump, and so any sharp jump in a wave will kind of oscillate in the filter, kind of like if you hit a spring, the spring jiggles a little bit. Well, so does a sound wave when you get the jiggly part of the sound wave and feed it back into itself. At some point, when you increase that feedback so much, you have the output of the filter going back in the filter and being so strong that the filter is just being overpowered by this continued feedback. And then at some point, it's so overpowering that anything that goes into the filter is immediately drowned out. And the output of the filter, what you're feeding back into it, has enough energy that it keeps going through the filter over and over and over. So the last thing that's on here is well, actually besides these, I have 2 toggle switches, which I'm not going to tell you anything about now. They'll be, once everything's done, I'm going to reveal what they do. But this is just a pure digital clipper, so it cuts off the top. And so as I increase it, things will look less smooth, and they'll start hitting the top of their limit values and then cut off. Let me lower this one. So see that got clipped? There's a sine wave. And square wave doesn't matter. Doesn't do anything. Triangle wave. And like I said, the sharp corners, or the sharp vertical sort of bits, is only achievable through adding high frequency content. So with these smoother things like sine waves and the triangle wave, as you distort it, you're adding in higher harmonics to it. So you can hear the pitch, like higher pitches appearing as you do that. Alright, so that's a filter. So now you can make some really sweet sounds.